to use this lecture hall to give a department colloquium. So Carleton got his bachelor degree in 1966, Harvard University in physics and chemistry, and his PhD at Berkeley in 1970. He then moved to MIT for postdoc position and later became a faculty member there. In 1978, Carleton moved to Utah and stayed here ever since. That's almost 35 years. So this summer, when Dave Kita into his position, accepted the position as the dean of the graduate school, so Carleton became our department chair. And as a tradition of the department, so the chair will tell us the great things happened in the department. So Carleton. None of the bad.
Yeah.
Also bad.
Right now. Thank you. Thank you. So this isn't going to be like the President's State of the Union address where we have all the Republicans on one side and the Democrats on the other side, because I think yes, I heard that. Okay, so this is a tradition we have here, so we'll keep with the tradition. I wanted to start off with some remembrances because we've lost in the last year 5 members of our community. Just to remind you, Jim Ball, just a couple of weeks ago. Al Larson, who was a technician in the cosmic ray group for a great number of years. John Viner, who taught in our undergraduate labs for a great number of years. Wayne Wingert, who was a technician in the optical electro materials group. And Norma Swigert, who was wife of Professor Swigert, who was a professor here for many years, and she was a great friend of the department. So on a happy note, we have new faculty members. First, Yan, Sarah Lee, would you like to stand up and wave so people can see you? Welcome. And Vikram Deshpande, who has not shown up yet. We hope that he will be here this fall. He's been working on visa problems, so it's not entirely his fault. Then we have a couple of faculty promotions. Andrei Rogachev was promoted to associate professor and was awarded tenure. Andrei, are you here? No? Okay, well, anyway. And Christoph Burma. Well, I'll send him an email. And Christoph Burma became full professor. And Christoph is a conference, so he can't be here. All right, great. Then we have a couple of administrative appointments. Richard Ingebretson was appointed Associate Dean for Student Affairs. Is Richard here? No. And Christoph became Associate Chair again. Thank goodness, because then at least there's some continuity here. And then, of course, we have our revered Dave Kita, who became Dean of the Graduate School. So if you need a football ticket, for example, he has friends. He has friends. Yes, and then there were some staff changes. So we have a new staff member in the accounting office, Josh Tomlin. Is Josh here? I should have brought a picture so you can see him. And Kelly Moulton has left. Let's see, are there any others from the accounting office here? Kathy Blair and Vicki Nielsen and Dina Young. Anyway, they're important. Yes, they're busy working on our payroll right now. Yes, I'm sure. Okay, well, maybe we should also see if there are any other staff members here from the main office. No, let's see. Sean, yes. This is an important person. Sean Merrill, hiding behind the box up there for half of you. And Thomas, yes. Yeah, Sari is standing in the back there. You can recognize her from her hair color. And let's see, it's great. And then Vicki Nielsen, that's from the accounting office. Then Jackie Hadley, no?
She's cleaning up after the...
Yeah, okay. The mess you guys made upstairs. And Heidi is out, yes. Even the crumbs, yes. Okay. And then, of course, Lynn Higgs, who does advising, is in the back there raising his hand. We have some new postdocs arriving. Maybe I should just have all of the new postdocs just stand, and then we could be recognized as Hee-Chung Na is here, and Matt Olmstead, and let's see, that's 3, 4, I'm not sure I know all of your names yet, but anyway, stand and wave. So welcome to the department. Maybe have a little applause for them. And then new graduate students. So we have altogether 19 new graduate students. 11 of them are domestic, 8 of them international. They come from Nepal, India, China, and Ukraine. Could these graduate students, the new ones, please stand? There we are. Welcome. So that brings our total enrollment to 96 PhDs and 2 master's students, so that's 98, almost 100 graduate students. Of course, the numbers don't continue to go up because we award degrees also. So we have, in the past year, awarded 12 PhDs and 2 master's degrees at last count. So just a brief comment. This is for the state of the department. We have to say something about things like the budget, I guess. So I cobbled together a few words here. I'll learn more about this as time goes on. But as we know, the economy, national economy, is improving slowly. So is the state economy. The science, technology, education, and math support from the legislature at the university is still, in my opinion, weak. They made some effort last year, but it's still not as good as we'd like. And as you know, federal funding is also very tight. Research grants are more difficult to get. And this has some consequences because the overhead, facilities, and administration pool of money at the university has been shrinking. And this is money that funds startup packages, tuition waivers, and the Center for High Performance Computing, and lots of other things. And so there's going to be budget pressure there. So we're going to manage, of course, but we have to be frugal. Enrollment, student enrollment in classes. As you all know, there's been a lowering of the LDS missionary age, eligible age for becoming a missionary. And that is expected to produce a dip in our enrollment temporarily. Because the younger folk as well as the older folk are off on missions. And there are indications already across campus that this is happening to some extent. But in physics, our fall 2013 enrollment looks very good so far. We may yet see a larger impact in the spring semester, but at least in the fall semester, we're looking pretty good. So that's the good news. Now I want to talk about some event highlights from last year. We'll start with some conferences. So last year we had Snowpack 2013. This was organized by a number of members of our department. And there were 3 parts to this. One involved black hole fingerprints and dynamics, disruptions in demographics. There was Snow Cluster, which dealt with galaxy clusters, and Snow Dark, which dealt with dark matter, all of them happening in March. Great time of the year for conferences and skiing at the same time, as you can see from their conference design logo. Then future conferences that are organized by department members include a small one called the Trevor Fest for Trevor Weeks, who is involved in the Veritas project, and that's being organized by Andy Smith in October. There's a conference on undergraduate women in physics being organized by Pearl Sandick in February, this coming. And in the following fall, Jordan Girton is organizing a conference on near-field optics and so on, NFO 13, which is going to be a big one. There's a little advertisement for the conference. NFO 13 includes nanophotonics and related techniques. They expect about 400 attendees from all over the world. So that will be exciting when that comes. Then I should mention this is not being organized by our people, but still I want to mention this as another upcoming conference. This is very soon, the APS Four Corners Conference. And this is for all of us, especially undergraduates and graduate students. It's very good to attend this. This is a section of the American Physical Society, sectional conference. So it has the blessing of the American Physical Society. You can apply for travel assistance from the APS and from the graduate school. Postdocs can also get support from the graduate school if they want to attend. That's a little known fact. And it's a great opportunity for professional growth for our students and postdocs, and faculty also are invited to participate. So I also have the URL in case you want more information, or you could just Google APS Four Corners. So another event last year, now returning to highlights of last year, the university became a member of Sloan Digital Sky Survey 4, I guess is what it's going to be called, Beyond 3, right? This was accomplished through a grant, a $350,000 grant from the Willard L. Eccles Foundation, and then a match from the University of Utah. So that was quite an honor. And what this does is it makes the University of Utah one of the lead institutions. It provides early access to data, which is essential for the research in the field. And so we have to thank Adam Bolton and Kyle Dawson, among others, for helping to arrange this. Other events, we have a whole series of outreach events. We're very active. We have a very active outreach program. I'm not going to read all of these. You can look at them yourself, starting from star parties every Wednesday night, going through access program, REU. Lots of physics shows that Adam Beeler puts on. Astronomy talks that Anil Seth has done, and so on. Many, many of these. So the community should know who we are. Other events of the last year, the astronomy group moved from the 4th floor of INSCC to the 3rd floor. The South Physics 4th floor remodel is winding, I guess it's nearing completion now. This is a space for student astronomy and also outreach astronomy, the star parties. And it will also have the capability, there'll be some control panels for controlling the operation of the Frisco Peak telescope, which is kind of exciting and interesting. So that's their mission control center. South Physics, they've gone through a lot of disruption, replacing pipes in there so that they can run the heating with hot water instead of steam. And as you can see from this beautiful upgrade to the room, the rotunda area, all of the lecture halls here have been upgraded. Nice new seats and carpeting and flooring and so on. So those were major events for remodeling. Now I wanted to pay specific attention to the REU program, which we started this year. And thanks to Saviz Safarian, who helped to organize this. We had, is it 10? Yeah, is it 10 participants in this program? And it culminated in a symposium. There's some pictures from this. One of the students here, Laura Beard, was working with John Bells and was selected to represent the REU program at the annual NSF REU conference even. Now, we have a number of faculty members and I guess also other members of the department who received new funding in 2012 and 13. Of course, there are others who have ongoing funding, but I'm mentioning just the new events. So Adam Bolton has a DOE Early Career Award and also some money from NASA. Savi Safarian, as I mentioned, is the PI on the NSF REU grant. Jordan Gerton and Shante Dimyad had money from the University Research Corporation. There are three more astronomers here who also had NASA money: Joel Bronstein, Inez Ivins, and Anil Seth. And then Dave Kita had some MRI money. Tabitha Bueller got some money from SPIE Education, and Tino Nyawelo had some money from the Refugees Program. So the 3-year average for all research funding in the department is a total of $4.8 million, which is a pretty hefty figure. That includes the MERSEC money. So that's a very good number. Various members of the department received honors. Shanti Dimyad got a University Research Foundation seed grant. That, I guess, okay. I got a Distinguished Teaching Award. Charlie Ray was named honors professor and also got a College of Science professorship. Alex Thiessen got a graduate research fellowship. And then Dave Kita got the University Distinguished Scholarly and Creative Research Award and also the Governor's Medal of Science and Technology. Jordan Gerton received the Scialog Fellow Award. And as I mentioned, Adam Bolton, an Early Career Award, which is not only money, but quite an honor. And Rhett Zollinger got a Student Research Award from the NASA EPSCoR program. So, priorities for 2013, 2014, things that I think the department needs to focus on. First of all, we have a graduate review coming up. This is the graduate school that requires every few years, every graduate degree awarding program on campus undergoes a review. And this involves a fair amount of work putting together a self-study. And then we have people from campus who come around, a committee of 3 usually, whom we meet with and discuss our program, and they read our self-study. And then we have external reviewers, and these dates are in early and mid-November. So some of the faculty members there, most of the faculty members will be invited to meet with these reviewers and talk with them about their view of the department and what needs to be done to improve it, what's good and what's not so good. Curriculum, we started a project of revising the undergraduate major tracks in order to make them more flexible, and particularly also to work on being able to offer some kind of a degree program in astronomy, or at least some kind of an emphasis in astronomy and astrophysics, and that's a project that I think we need to continue pursuing. Then there's the new building project, which went through a preliminary study with the architects MJSA. They completed their study earlier this year. It's what we would consider an example of what we could do, the preliminary design. It was helpful for setting the scope of what we might need. A completely new building is still an option, but the path forward requires integrating our needs into the campus master plan. So this is something that takes a long time. Don't expect that you come back next year and we'll be in a new building. It takes 10 years, 15 years for these things to happen. And it also requires concerted fundraising in order to make this happen. The more we can raise, the more attention we'll get from the campus designers. So that's a long-term project. Another tradition that Dave started I'd like to continue is to go through some research highlights of our faculty. So I want to spend about, well, half hour or something like that, talking about what our faculty have been doing. Everybody, I thank everybody for making contributions and sending me slides. There's a lot here, so I'm afraid I'm not going to be able to do everything justice, but I'll see what I can do. So we'll start with condensed matter theory, and Alexei Efros. Is he here, possibly? Ah, oh, okay, so I can say what I want, can I? Anyway, so he's been working, he sent me some slides about some work he's been doing on an ordered array of nanocrystals. So these are not just atoms anymore, these are nanocrystals. And they have some interesting properties. That should be O of nanocrystals. And so one of the issues has to do with electron mobility, which is risen by more than 4 orders of magnitude, it says here. I guess that's an observation. And so he's been studying that and the reasons for why that happens with photoexcitation and without, so photoconductivity and also without light. I think I won't ask you to read this summary, but just to give you a sense of what he's been working on. Condensed matter theory, Eugene Mishchenko sent me a slide about his work on dipole-induced localized plasmons. So the plasmons run around the surface, but if you have a dipole on the surface, then they can be localized, as I read the slide, making a kind of a nanoparticle. And these lead to resonant enhancement of scattering of surface plasmons off of the dipole. And on the bottom is this possibility of controllable plasmon propagation. Did I do that? Is Eugene here? Did I do that justice?
Yes, thank you.
Okay.
If only you would be my referee.
Yes. Yes. Another condensed matter theory, Oleg Starik. He likes to work on frustrated systems. These are systems with a 3-fold coordination or 6-fold. And so if they're anti-ferromagnetic, they like to be anti-aligned, but you can't do that if you go around the triangle. They can't all be anti-aligned, so that makes it frustrated. And there's some interesting work that, these are titles of 3 papers in Phys Rev. 2 in Phys Rev and 1 in Phys Rev Letters, in fact. And he wanted me to advertise this research position here, research assistant position available immediately for qualified graduate students. How many? How many? You'll have to ask Oleg. You'll ask him. So that's interesting stuff. So. And then Misha Reich, condensed matter theory. Maybe if Misha is here, you can explain. Would you like to?
Can you?
Can I explain? Well, is this an exam? Okay. So this is about negative spin memory loss. Now, I love the idea of negative memory loss because it helps, because it means I've remembered something that I almost forgot. No. Negative tunnel magnetoresistance. This has to do with spin orientation and resistance. That's what I'm gathering from looking at this, and maybe you can help me with the rest of this. Interference, yes. This is a quantum effect.
Yes.
Yes. Okay. Yeah, it is. No, it's just very interesting. In fact, if the Tribune finds about it, it'll be in the headlines tomorrow. Okay. Condensed matter experiment, let's see, Professor Alien wanted me to mention that he's been treasurer recently of the International Society for Magnetic Resonance, which is an honor and also a fair amount of work. Putting the house back into order, as I understood.
I should add that the next meeting will be in Shanghai in 2 years, so hopefully you can all come to that.
Uh-huh.
Last one was in Rio.
So. Then Professor Burma, condensed matter experiment. And there's a lot on this slide, so I'm not going to try to go through all of this. His research focuses on manipulating spins and on exploring mechanisms that enable the control and measurement of electron or nuclear spins in weakly coupled spin orbit materials. And one of his recent projects that he wanted me to mention particularly is this work that he's been doing with Clayton Williams on spin microscopy. So running around on the surface and actually detecting, well, in the end, ultimately individual spins would be the goal. They aren't quite there yet, but they're almost there. So it's a very interesting project to be able to actually identify and locate individual spins on the surface. Condensed matter experiment, Professor Dimyad has a group mainly working on high pressure properties of matter under high pressure. Here we have a phase diagram for lithium on this panel here that they've been working out. And there's a long list here of lots of highlights that she sent me, which I'll let you read. There's even a very interesting one. Oops, as I went backwards. Very interesting one on the bottom. This is NASA astrobiology, which is quite interesting. Very high pressure systems. Jordan Girton. So he has a couple of projects. This one is a project that is designed to improve the efficiency for producing hydrogen gas in electrolysis using light in the solar spectrum. And so using gallium, this is gallium, G-A-N, gallium nitride, I guess it is, nanowires for solar spectrum matched photoelectrochemical water splitting. And so he's got a grant proposal into the DOE. This is something, of course, that would be very interesting for energy production, energy use of alternative energy sources. And so that should be interesting to the DOE. Anyway, he's got a proposal in preparation for that. Then he's also been working on preparing TAs for leadership in STEM education. So there's a conference, first annual National Teaching Assistant Workshop next May. He's got 2 conferences under his belt. This one is at least happening elsewhere at Georgia Tech. So facilitate the adoption of interactive evidence-based teaching and learning strategies by harnessing the immense potential of teaching assistants. Then Vali Vardini sent me a couple of slides on organic magnetoresistance at small magnetic fields. What this is doing is, what one can do with this is make a device that will tell you the direction of the magnetic field, like a compass. Last year we heard Christoph Burma talking about some work that he and his group had been doing, making little devices for measuring magnetic fields. And so this is done with organic magnetoresistance. And then Clayton Williams sent me a slide on looking at electron transfer and imaging. Is Clayton here? Yeah. You want to say a word about this?
Well, yes, we're using the technique that we've developed in the last decade to measuring single electron tunneling events, and we are now trying to tunnel to molecules that are on insulating or dielectric surfaces to basically map out the wave function of those molecular orbitals, measure the
Good. And so he's got a picture of ferrocene dicarboxylic acid molecular ions on calcite here. This can be seen in the atomic force microscope. Then in astronomy, Adam Bolton has been working on gravitational lensing with SDSS spectroscopy. Did you want to, Adam, you want to say something about that?
I'm back here.
Oh, you're there, yes.
Hi, yeah, so this is one of two different themes that we're working on in our group, both beginning with Sloan spectroscopy of many hundreds of thousands of galaxies, and in this work we look for the 1 in 1,000 or so that have two galaxies along the same line of sight. If you look at those with the Hubble Space Telescope, you can see this phenomenon of strong gravitational lensing, which is really the most powerful way of measuring the mass of galaxies at cosmological distances. And there's various ongoing work that we're doing to use those measurements to learn about the structure and evolution of massive galaxies.
And then there's dark energy spectroscopy.
Yeah, so this is the other 999 out of 1,000 galaxies going into this. And the ultimate goal here is to learn about the nature of dark energy as traced out by the large-scale structure of galaxies in the universe and how that evolves with time. But of course, in detail, there's a long chain of inference from the observations through the raw data and calibrations and spectra and measuring redshifts and classifications, building three-dimensional maps of galaxies in the universe. So this is something that a lot of us here are involved in, and part of a very large collaboration in the Sloan Digital Space Survey to make what are really some of the most competitive dark energy measurements that are currently going.
Good. Then we have planetary physics with Ben Bromley. And this is interesting stuff because they're figuring out how microscopic dust particles aggregate and eventually build up to make larger objects, and finally those objects in turn make planets. So that's a combination, interesting combination of nanoscience and astrophysics. And if you look at the names on the list here, it includes Jordan Girton, who's a condensed matter experimentalist, as well as astrophysicists. Ah, is Ben here? Yeah. That's the bolide. Is that the bolide in Siberia? Okay. Yeah. Great. That's a beautiful picture, by the way. That's taking it apart instead of building it up, though, right? Yeah. And so here's another one. You want to say a word about that?
Sure. We have a group of us doing dynamics in theoretical astrophysics. The panels that you see on the right are some of the projects we have going. Ben Kaya is mapping out with a relativistic ray tracer the effect of the collect potential on cosmic radiation. Leah Abdopoulos is looking at how stars interact with each other and a central black hole toward understanding black hole growth.
Okay, now in cosmic rays, John Bells has been developing, he and his group have been developing a very interesting new way of detecting cosmic rays. And this is to use radio waves, actually television frequency waves, and bouncing and attempting to bounce them off of the ion trail that's left by a cosmic ray shower in the atmosphere. And so they've got, this is called TARA for radar detection. I guess it's the radar frequency detection of cosmic ray showers. They've got an experiment set up out in the West Desert, and they're starting to test the method. Then we have biophysics and Savis. Here the goal is to understand, as the slide says, how viruses are put together. So he's studying the budding of HIV and other viruses. Is Savis here? You could say a few words.
Yeah, so the goal is to take the virus apart and see what are the replication machineries that help replicate so fast,
Yeah.
both for HIV and for VSV.
And I see that you're also doing high pressure physics, like Shanti. Yes, yeah. Then Michael Verschinen has been working on molecular motors and looking at ways of inhibiting their motion. So kinesin is one of the molecular motors in biological systems, an important one for transport in the cell. And so he's been looking at one device for inhibiting motion. Is Michael here? Did I say that right? Did I say it?
Basically, I run a lab over at pharmacy. They purify some compounds which are completely novel, nobody has seen before, but they're from a class of compounds which were known to affect transport. So we're pretty much the only lab on campus that could do that. So we looked at how it affected transport, and really it was Tom was sitting over on the other side and did a lot of that work. So he found very strong inhibition, and interestingly enough, different inhibition, which is not shown here, for different classes of motors, which is going to be very exciting going forward, and also resolved some issues with whether this was aggregate activity or one-on-one chemical activity. So there was a lot of data in this slide.
Good. Yeah. Mathematical physics, I guess we can call this. Yongshi's group has been looking at topological matter and exactly solvable discrete models in two spatial dimensions is what's involved here. This has some, I guess you could call practical interest in topological quantum computation. So there's a lot of interesting mathematics here, as well as applications in possible applications in condensed matter physics, as well as in quantum computation. And Yuting Hu, his graduate student, just recently defended his thesis successfully, working on some of this stuff. The two slides here. So various topics in topological properties in two-dimensional matter. Medical physics, Werner Gellermann has been doing, over the years, been developing laser systems for doing assays of pigments of various kinds in the retina and also human tissue. And this has some very immediate medical applications. Of course, it takes a long time to develop these things, but there are a number of patents that they have filed for these processes, and they're used for diagnosing the health of human retina. And then theoretical high-energy physics. Pearl Sandick has been working on dark matter. She even provided us a picture. That's what she looks like with a hard hat. And that's her postdoc, Chris Kelso, also in a hard hat. I guess that's from visiting one of the underground laboratories. And so first there's a question of the direct detection of dark matter. and people have been doing experiments trying to observe these. And as they either find something that looks possible or they don't see something but they put upper limits on them, one can then put constraints on various models. And so that's what this figure here represents, a constraint on some parameters of a model that is obtained from analyzing the results of the experiment. And then also looking at supersymmetry phenomenology and looking at indirect detection of dark matter. So the other was direct detection, where you have the apparatus and you look for a bump that happens when the dark matter runs through it. Indirect detection is looking for various unusual phenomena in satellite observations of things like electron spectrums or gamma ray spectrum. In this case, it's the gamma ray flux. One of the experiments, the so-called Fermi-Lab experiment, found a little bump here, which is hard to explain and maybe has something to do with dark matter, or maybe it's just an experimental artifact. But these are things that are intriguing and worth study, just to see whether or not they fit the models that you might think would be plausible. More on supersymmetry phenomenology. Pearl said not to spend too much time on these because she's giving a colloquium in another couple of weeks on this subject. Then this was going to mention one project of mine. This is a project that Sui Chu, a graduate student of mine, has been working on with me and with the rest of our collaboration, which is nationwide collaboration. We've been using, trying to determine some key parameters of the standard model. Those parameters include things like the electron mass, but the parameter we're looking at is one that's relevant to the decay process where a B meson, which has a B quark and an anti-up quark, decays to a charm. This turns into a meson that has a charm quark and an anti-up quark. So B turns into a C, emitting, say, an electron and a neutrino. And that process of the B turning into C, it gives one parameter of the standard model called BCB. You can get this by doing a theoretical calculation and matching it to the experiment. And that's what this shows. The blue stars are the experiment. The blue band is the theory. And the shape matches very well. And the normalization gives us this constant, which is a determination of that constant. It has not been done before using this particular method. And that's it. So those are our highlights. And we have an amazing research program going on here in our department. And I hope that we're going to be having more highlights. I certainly look forward to more highlights next year. So thank you. Now, before you go, Adam Beeler has a little demonstration he wants to show us. Let me see if Adam is here. Ah, there he is. Okay, Adam, take it away. I don't have to hold on to the electrode, do I?
We're doing tomorrow morning, and I like it.
Would you like this? When the folks back home can hear us?
All right. And this is also a demonstration that I think everybody needs to see at least once in their life if they haven't. So here's your control system. Which one hits the ground first, a feather or a ball? A feather. Woo! Okay. So now this contraption has an electromagnet up here. And so I'll set these on, maybe, on the platform, so that we can release them at the same time. And then, of course, it's easier to use a vacuum pump than take this to the moon. So we'll seal it off. There we go. And now I stall. So, and you know, you ask the students to predict. And this is often used when they want to discuss gravity, obviously. I prefer to do as in Newton's laws to emphasize that the acceleration due to gravity is constant, at least right here. And so the forces are different, though, in order to accelerate different masses at that same rate. So I have a switch on the side. I'll release it at the same time and count so you guys can watch. And I'll suggest you watch the lower half and verify if physics really is true. A lot of students try to follow it and then they can't tell. I think they landed at the same time. We'll see. This removes most of the air, and you can repeat it not pumping out as much air. And you can see an effect where the ball still wins, but not by as much. So I'm still stalling, and I think we're probably far enough now where we want to see we'll see what we want to see and what we expect. I'll get out of the way. 1, 2, 3. Woohoo! So physics is still true, and the department's doing great.